Warming up exercise. We have a single bay, post and beam deck. Consisted of planks. Planks typically are available in nominal width of 4 or 6 inches, but for the purpose of analysis, we will assume a unit width equal to 1 foot. So if we look at one single plank, it has a length of 8 feet and a width of 1 foot. So that's 1 foot. That will be tributary width of plank. So tributary width of plank is equal to width of plank, which is 1 foot. And then length of plank is 8 feet. The question is asking us to calculate the plank, beam, and column reaction. So we will look at free body diagram of a plank, calculate the load on a plank, and end reactions. These reactions are the loads transferred to the beam supporting plant. So these reactions are the loads transferred from each plank to the beam. So using free body diagram of a beam, we calculate end reactions, and then we have loads transferred to the columns. So basically, the load path is from plank to beam to column. And we will do the load tracing to calculate the ground reaction. What is the area load? That we have the total dead load and live load applied to this deck is 68. So that's the total dead load and live load pound per square foot, or PSF. Okay, so we start by looking at FBD of a plank with a width of 1 foot and length of 8 feet. The area load on this deck, or the total dead load and live load, is 68 PSF, and tributary width of plank is equal to width of plank, and it's equal to 1 foot. So the load on the plank, which you see here, is equal to area load times tributary width, which is equal to 68 pound per square foot times 1 feet, which gives us 68 pound per foot. Again, this comes from 68 PSF that we have, pound per square foot, times tributary width of plank, which gives us 68 pound per feet. So that's how much load we have on a plank. We need to calculate the end reactions. we have a symmetric system here, which means that R1 is equal to R2. We're going to use R. And previously, we went over an example for the use of equations of equilibrium. So we can say here, since this is a simply supported beam and it's symmetric, the reactions are equal to each other, and they're equal to load times length divided by 2, which gives us 272 pounds. £68 per foot times total length divided by 2. Now, the reactions that we have here are transferred to the beams supporting planks. So these are the loads transferred to the beams. Same magnitude, opposite direction, same line of action. So each plank, each individual plank transfers 272 pounds. Again, each individual plank does that. And the spacing between planks is 1 foot. So on the beam, we have, if we look at this beam, the load that we have on the beam is 272 pounds. The load on the beam is 272 pounds at 1 foot from each other. This is basically 272 pounds per foot, or 272 PLF. That's the load transferred from all of the planks to the beam. Each individual plank transfers 272 pounds, but we have planks at 1 foot from each other, so the load on the beam is 272 pounds per foot, which is 272 PLF. When looking at the beam, we also need to include weight of beam by itself. So beam has a dead load of 10 PLF. The total load on our beam is 272 plus 10. Now we can calculate the reactions. Again, simply supported beam, symmetric, reactions are equal to each other, and they're equal to 272 plus 10 times total length. The span length is 12 feet. So this times 12 divided by 2, which gives you 1,692 pounds. And that's our column reaction. So as you can see here, the beam is supported by columns. So if we look at a column, this is how much load transferred to a column. There's another way to solve the problem. In the previous slide, we looked at free body diagram of a plank, free body diagram of a beam, and then we looked at the column. There is another way, an alternative to solve the problem, and in this method, we skip free body diagram of plank. We look at the beam. So we are looking at our beam, and we say that we have an area. This is our area, and we have the area load, the total dead load and live load of 68 psf. Instead of looking at each individual plank, we look at the area and then say that this area is supported by two beams. Half of the load is transferred to the right beam and half of the load to the left beam. So we can look at tributary width of beams. Now, if we look at one beam and do FBD of the beam, tributary width of our beam is 4 feet. The area load that we have, so area load, dead load and live load, is 68 psf, and tributary width of beam is 4 feet. So the load on the beam is equal to 68 pound per square foot times 4 feet, which gives us 272 PLF, which is the same number that we had in the previous slide, but we used a different approach to do the calculation. And the reaction calculation is the same. We have a simply supported beam, symmetric, so the reactions are 272 plus 10 times total length divided by 2. And now we can look at the columns supporting the beams. This is the load transferred to the column. Now we need to look at dead load of column, which is 100 pounds. So the total ground reaction, this is our ground reaction, is 1792 pounds. Example number 1. This example is an expansion of the previous example, where the decking has an additional 6 feet span and the beams are extended another bay. So in the first example, we had the plank length of 8 feet and beam length of 12. Now we have an additional span and another bay. Loads on the structural system remain the same. The question is asking us to calculate the reactions located at grids 1A, 2A, 3A. So here we have 1, 2, and 3. Here we have A, B, and C. So we have the area. Area is supported with 3 beams, 1, 2, and 3 beams. And then we have the columns here, here, 9 columns. So the question is asking you to calculate the column reactions. We're gonna start by looking at beams along grid line A. So this is grid line A, and this is the beam along grid line A. The adjacent member, there is one adjacent member to beam A, which is beam B, and half of the distance between A and B, this is 6 feet, so half of the distance is 3 feet, and that's the tributary width for beam A. So this is A1, A2, and A3. Here we have 16 feet, and here we have 12 feet. We said that load is equal to the area load that we have times tributary width. So the area load is still the same. Dead load and live load is equal to 68. So it's 68 PSF times tributary width, which is 3 feet, which gives us 204 PLF. That is the load transferred to beams along grid line A. Pay attention that we need to include weight of dead load of beam in our calculation. So the reactions here are equal to 204 plus 10 times 16 divided by 2, and here 204 plus 10 times 12 feet divided by 2. The next member, or the members supporting beams along grid line A, are columns A1, A2, and A3. So we have a column supporting here, one here, and the third one here. This is column A1, column A2, and column A3. The same amount in the opposite direction is transferred to column A1, and same thing here. But when we get to column A2, pay attention that we have two reactions. We have reaction on the left side and then another reaction on the right side. So we need to add these two together to calculate the total load transferred to column A2. Now we want to look at beam along grid line B, and there are two adjacent members, A and C. So we need to look at half of the distance between A and B and half of the distance between B and C. So again, we are looking at beam B now. It has two adjacent members. Half of the distance between A and B is 3 feet, and half of the distance between B and C is 4 feet. So the tributary width for beam B is 7 feet. Now, how much is the load transferred from the area to beam B? The load is equal to the total dead load and live load that we have, which is 68 psf, times tributary width of beam B, which is 7 feet, which gives us 476 PLF. Now we need to do the calculation for reactions. Simply supported beam, symmetric, reactions 476 plus 10 times 16 divided by 2. And here 476 plus 10 times 12 divided by 2. Beam B. Beams along grid line B are supported by 3 columns. Column B1, column B2, and column B3. Same load, the opposite direction, is transferred to column B1. Same thing here. But pay attention again, when we get to the middle column, this column here, we have two reactions. One from the left side, one from the right side. So we need to add them together. So we add these two together to have the total load transferred to column B2. You can pause the video and try to do the calculation as a practice. Do the calculations to find the reactions or the loads transferred to column C1, column C2, and column C3. So beams along grid line C these two beams along grid line C. They have one adjacent member. Beams along grid line B, and half of the distance between B and C is 4 feet. The load is equal to the area load times tributary width. The reactions 272 plus 10 times 16 divided by 2 and 272 plus 10 times 12 feet divided by 2. And then finally, we have the loads transferred to column C1, C2, and C3. The opposite direction, same magnitude. Opposite direction, same magnitude. And again, one more time, when we get to the middle column, we have two beams sitting on that column. So you need to add reactions together to calculate the total load transferred to the middle column. So we have all the columns. Again, here we have A1, A2, A3, B3, C3, and so on. We calculated the loads transferred to the columns, but pay attention that we also have a dead load for our column. So the column weight by itself, the column by itself weighs 100 pounds. So if the question is asking for ground reaction or foundation reaction, you need to add dead load of column, which is 100 pounds, to the load transferred from the beam to the column. So for example, for C3, the load is 1692. The ground reaction is 1792 pounds. For A1, the load transferred to the column is 1712 pounds. The reaction is 1812